1 0, the first column. Then the coefficient of x2 in first element is -2 and here -1, so that's why -2 -1, right? Since B is the standard basis of R2, the transition matrix P from B to B dash can be written as P is equal to 2 minus 3 1 4. Okay, 2 minus 3 1 4, because you can see, since B is the standard basis of R2, the transition matrix P from B to B dash, because of B is the standard basis, we can write directly, this is the first column 2 1 and this is -3 4. Okay, now determinant of P, you can easily find it. 4 into 2 8 minus -3 into 1, that is 8 plus 3, that is equal to 11, and adjoint of P, that is equal to 4 3 minus 1 2. Okay, adjoint of P, that is equal to 4 3 minus 1 2. How we write down this adjoint? Because just in 2 cross 2 matrix, just we have to interchange the main principal diagonal element, that is 2 4 can be expressed as 4 2, and we have to change the sign of the other diagonal elements, so 3 minus 1. Now P inverse is equal to adjoint of A upon determinant of A, that is equal to 1 upon 11, 4 3 minus 1 2. So the standard basis T with respect to basis B dash, that is equal to P inverse, the standard basis of T with respect to B into P, that is equal to 1 by 11, 4 3 minus 1 2, so 1 minus 2 0 minus 1, so 2 minus 3 1 4. So when we multiply this two matrix, just try to understand how we multiply the first two matrix. Just pick up the first row 4 3 and multiply with each column, so 4 into 1 4, 3 into 0 0, so that's why this is the first element 4. Then 4 into -2 -8 plus 3 into -1 -3, so -8 -3, that is -11. Then now we multiply each column with the first row. Now pick up the second row, so -1 2 and multiply each column, so -1 into 1 -1 plus 2 into 0 0, so -1 -1 into -2, that is 2 plus 2 into -1 -2, so 0. Then 2 minus 3 1 4, 2 minus 3 1 4. Now 1 by 11, 4 into 2 8 minus 11, that is -3, 4 into -3, that is -12, minus 44 minus 56. Then -1 into 2 -2, 0 into 1 0, -2, and -1 into -3, that is 3, plus 0 into 4 0, so 3. So this equal to -3 by 11, minus 56 by 11, minus 2 by 11 and 3 by 11. Okay, so next example, next. Consider the basis, this is a question 4C. Consider the basis S, that is equal to V1 V2 of R2, where V1 is equal to -2 1, V2 is equal to 1 3, and T from R2 to R3 with a linear transformation such that T of V1, that is equal to -1 2 0, T of V2 is equal to 0 -3 5. Find the formula for T of x1 x2 and use that to find T of 2 minus 3. So what is our target? We have to find the formula for T of x1 x2, right? That is our first target. We have basis vector for the domain and we have image vector of that basis vectors. Okay, so what is our target? V1 and V2 are basis vectors, correct? Now and R2 basis vectors of R2, that means what? Any vector of R2 can be expressed as linear combination of V1 and V2, right? Any vector of R2 that can be expressed as linear combination of V1 and V2. So that's why we use first of all that property, that step that if V is equal to xy is a vector of R2, then V can be expressed as linear combination of V1 and V2. So V is equal to K1 V1 plus K2 V2. So xy, that is equal to K1 V1 is minus 2 1 plus K2 V2 is 1 3. Okay, so minus 2 K1 plus K2 and then K1 plus 3 K2, right? This gives 2 K1 minus 2 K1 plus K2, that is equal to x. Comparing this to left hand side and right hand side, so minus 2 K1 plus K2, that is equal to x, and K1 plus 3 K2, that is equal to y. Solving these two equations, easily we can find K1 and K2. So solving this equation, we get K1 is equal to y minus 3x upon 7 and K2 is equal to x plus 2y upon 7. Okay, here we have just two equations, so directly we can solve these two equations and we can easily find K1 and K2. But suppose we have three equations, right? Suppose our domain is not R2 but R3, so definitely we have three basis vectors, right? So corresponding to that three basis vector, here we get three equations, right? If our codomain is also R3. So solving these three equations, we have to use matrix method, right? Just write down the augmented matrix, that augmented matrix convert into a row echelon form, right? And using that row echelon form, we can easily find the value of the coefficients, right? Like K1 and K2 here we find, right? So but here we have just two equations, so we can easily find out K1 and K2, right? We don't need to use that matrix method. Using that matrix method also we can find K1 and K2, but it's quite easy to solve directly, right? So K1 is equal to y minus 3x upon 7 and K2 is equal to x plus 2y upon 7. Now put this value of K1 and K2 in equation 1. Okay, so equation 1 become xy, that is equal to y minus 3x upon 7 into minus 2 1 plus x plus 2y upon 7 into 1 3. Okay, so t of xy, that is equal to y minus 3x upon 7, that is t of minus 2 1 plus x plus 2y upon 7, that is t of 1 3. So y minus 3x upon 7, t of minus 2 1, that is minus 1 2 0 plus x plus 2y upon 7, that is 0 minus 3 5. Okay, so multiply this in this coordinate, so we get 3x minus y upon 7, then minus 9x plus 4y upon 7, and then 5 into x plus 2y upon 7. Okay, so it's quite easy to solve this example. And now also we have to find t of 2 minus 3. So just instead of x we have to put 2 and instead of y we have to put minus 3. So we get 9 by 7 minus 6 by 7 and then minus 20 by 7. Okay, so just put 2, so 3 into 2 6 plus 3 9, so we get 9 upon 7, then minus 9 into 2 minus 18 plus 4 into minus 3 minus 12 minus 18 minus 12 minus 30 upon 7, sorry, minus 9 into 2 minus 18, okay, plus 4 into minus 3, so minus 12, so that is minus 6 by 7, and then 2 plus 2 minus 6, that is minus 4, right? Minus 4 into 5, that is minus 20, so minus 20 by 7. Okay, so here we get 9 by 7 minus 6 by 7 and minus 20 by 7. So here the complete the solution of this question. The next question, question 4d, define kernel of T. Let T from R2 to R1, right? P1, T from R3 to P1, where P1 means set of polynomial of first degree, 1 degree. So set of polynomial of 1 degree be the linear transformation defined by T of a1 a2 a3, that can be expressed as minus a1 plus 2a2 plus a3 plus minus a2 plus a3 into x. Find which of the following vectors are in kernel of T. So what is the definition of kernel of T? First of all, try to understand those vectors from the domain, we have to collect those vectors from the domains such that image of that vector that is equal to 0 vector, right? So if suppose our transformation, linear transformation T from V to W, right? So those vectors we have to collect from the domain V such that image of that vector that is equal to the 0 vector. Okay, so that's why one by one we have to check that for these three vectors how many are in kernel of T and how many are not, in the kernel of T. So here is the first definition: let U and V be two vector space and let T from U to V be a linear transformation. The set K of T of all premises of 0 belongs to V, right? So kernel of T set theoretically we can write in this manner, as I told you, X belongs to U such that T of X is equal to 0, where 0 is a 0 vector of the codomain, not a domain. Okay, it can be possible that the 0 vector for domain and codomain are different because of domain and codomain are different sets, right? So for the different sets definitely we have different 0 vectors, right? So this 0 is a 0 vector from of the codomain, right? So we have to collect all the elements from the domain such that image of that domain, image of that elements are exactly the 0 vector of the codomain. So that's why the kernel of T we can write set theoretically in this manner. Kernel of T is equal to X belongs to U, where T of X is equal to 0 is called the kernel of T. Now it's quite easy to check that for these three vectors are in kernel of T or not. So just check T of 6 to 2. Already we have T of A1, A2, A3 how we defined in the definition, right? So just put 6 to 2 instead of A1, A2, A3 in the definition. We can write minus 6 plus 4, 2 into 2 4 plus A3, that is 2. So 0 plus 0 into X, so we get 0, right? So definitely 6 to 2 belongs to kernel of T. Now T of 2 minus 1 1, that is equal to 2 minus 2 plus 1 plus 1 plus 1 into X, that is not equal to 0 because of here we get minus 4 plus 1, that is minus 3, and this is minus 3 plus 2x, so that is not equal to 0. Okay, so 2 minus 1 1 is not belongs to kernel of T. The third vector T of 0 0 0, that is equal to 0 plus 0 plus 0, that is equal to 0 plus 0 into X, that is equal to 0. So definitely this 0 vector of the domain are belongs to the kernel of T. So basically kernel of T is a subset of domain, right? Because already we have collect all the elements from the domain. Next question, question 4e. If U and V are orthogonal unit vectors, then what is the distance between U and V? Justify your answer. Here is the solution where U is to quite easily understand, we use set of vectors of R3, x1, x2, x3, and V is V1, V2, Y1, Y2, Y3. So if U and V are orthogonal, it's clearly that inner product UV is equal to 0 by the definition of orthogonal vectors. So when inner product U with V is equal to 0, that means what? Using Euclidean inner product, x1 y1 plus x2 y2 plus x3 y3, that is equal to 0. Okay, so distance of UV, that is equal to under root x1 plus y1 square plus x2 plus y2 square plus x3 plus y3 square. Okay, so under root, that is equal to under root x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square minus 2 into x1 y1 plus x2 y2 plus x3 y3, right? So under root x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square okay, because of x1 y1 plus x2 y2 plus x3 y3 is equal to 0, we have, so this term, this will be cancelled out. So only we equal that this equal to under root x1 square plus x2 square plus x3 square plus y1 square plus y2 square plus y3 square, and that is equal to under root summation xi square plus summation yi square. Now that can be expressed as, because of we know that norm u square, that is exactly under root inner product u with u, so under root u square plus under root v square, that is equal to under root 1 plus 1, and that is equal to under root 2. Okay, here is the next question. Define algebraic multiplicity of an eigenvalue and determine the algebraic and geometric multiplicity of A of this matrix 0 1 1 1 0 1 1 1 0. If the eigenvalue of A r lambda is equal to 2 minus 1 minus 1 and corresponding eigenvectors for lambda is equal to 2 is 1 1 1 and for lambda is equal to minus 1 r, there are two eigenvectors minus 1 1 0 and 1 1 minus 2. It's quite easy to understand because what is algebraic multiplicity? Here is the definition. The algebraic multiplicity of an eigenvalue lambda is multiplicity as a root of the characteristic equation A minus lambda is equal to 0, and right. So algebraic multiplicity of A is 2 because as an eigenvalue lambda is equal to minus 1 is repeated twice. The algebraic multiplicity of minus 1. Okay, so the algebraic multiplicity of minus 1 is 2 and the geometric multiplicity of minus 1 is also 2 because of corresponding to minus 1 we get two eigenvectors. Now from of 2, the algebraic multiplicity of 2 is 1 because as an eigenvalue the 2 is considering only one time, right? 2 is considering only one time, so that's why the algebraic multiplicity of 2 is 2 is 1, and the geometric multiplicity of 2 is also 1 because corresponding to 2 we get only one eigenvector, so the geometric multiplicity of 2 is also 1. Okay, so up to question number 4 if we solve this question paper. Thank you.